Okay, great. Okay, so one of the things that you need in order to be able to use tables is to do interpolation. So this comes up in two ways. One way is you do interpolation when you're using the tables, and so you want to know sine of some angle which is not in your table. And sometimes also you want to use interpolation when making the table. So we're going to see that later on that there is only certain angles where you can get super accurate values for, and somehow you've got to want to fill in your table. So you need to do interpolation for those. Okay, so the simplest kind of interpolation is linear interpolation, and I'm sure any of you have anything to do with tables have used linear interpolation. So for example, if you've ever done statistics and used the normal distribution, you've probably done some kind of linear interpolation there. So these is tables of al-Biruni from his Masudic canon. So it's called that because this shows like the influence of patrons. Masud was the son of the king, and so al-Biruni named his work in honor of this, and it just shows, you know, the patronage system. So this is the Ghaznavid dynasty, and this is so this is, you know, the Abbasid Empire is starting to break off. So the Ghaznavids were kind of to the east. I think they were sort of northeast Iran, and then going into the stans like Uzbekistan and Kazakhstan, that kind of area there. So they were one of the first areas kind of to break off from the main Abbasid Empire. But still, you know, it's a very learned place. Like, for example, Samarkand is there. This is sort of ancient city there, the seat of learning. Okay, so here is his tables. Can anyone notice anything interesting about how this table is read? So here we read a table left to right. Can anyone see what's happening up here? Nope, not top to bottom. It's still, you know, these sort of correspond to those. But here we can see 0, 0, 0, 1, 1, 1, 1 quite easily. And here we can see 0, 0, 0, 1, 1, 1, 1. So this is read right to left. Anyway. So remember, sine is a function of arc. It's not a function of angle like it is for us. So arc, by that we mean the function of the circle, the part of the circumference of the circle. Sine is always a positive number. So not like us, we don't have to remember the little acronym to figure out when a trig function is positive or negative. For them, a trig argument is always positive. This actually causes a little bit of problems, right? Because if you actually want to prove things, it turns out you have to break up things into different cases depending upon what quadrant the angle is, because whereas if you just do our treatment of the trig functions, quite often arguments are very general and they hold for all possible angles. Okay, he is using r equals 1, right? And we can see this, right, because 1 degree, sine of 1 degree is around 1 minute, is around 1/60th. So that's showing that r is 1. And I'm sorry, some of my pictures don't seem so good. Some people were complaining about one of the problems with doing the parameters of sun. Someone found you hard. Sorry about that. Anyway, so what is this table doing? So we see that here we have the arc, here we have the sines, and we see that it's 4 places. So quite up. Then we have a column called the differences. So you know that if you're going to do linear interpolation, so basically you want to know how much is between your entry and the next entry, and then you're going to do a corresponding fraction of that thing. So the difference is then just how much is the difference between that, you know, this is that minus that. So it's already setting you up so to help you do interpretation. And then he's got the corrections, which is 4 times the difference. And it turns out that that is what you use to do interpretation. So if you want to figure out sine of something, then you go to the lowest sign that's in the table, and there you take the number of minutes that you're doing it, and you multiply it by the corrections. Okay, and this basically is the reason why it's 4 is 4 times 15 is 60, and we're doing things in base 60. So that's when you do the arithmetic, that's the number that turns out. Okay, so let's do an example. Okay. So from the table, we can see what sine of 1 degree in 15 minutes is. And we see that actually, no, it's correct, you know, to 8 decimal places. You know, so that the error is very small. So let's compute sine of 1 degree 22 minutes. Okay, that lies between 115 and 130. So we take 115, and it's 7 minutes more. So we do 7 times the corrections. And then we just go through, and it's 7 minutes, right? So everything is in the correct sexagesimal place. So we do this times this, so we can have a 0 first, right? Because we've got 7 minutes times 1 minute. A minute times a minute, the answer is going to be a second. So that's the seconds. So we do the multiplication, and then we go through and we carry things through, so we get what it is. And so we get the value. And what we've seen is, because we've done linear interpolation, basically we lose 1 decimal place of accuracy. So the error is kind of 10 times more. That's, you know, that's what happens when you do interpolation. How can we do better? Well, we can try going the next order up, quadratic interpolation. So assume, has anyone done any higher order interpolation? You have? Yeah, okay, good. You probably all have done a little bit when you did Calc 2, at least, when you saw Taylor polynomials. It's not interpolation, but it's quadratic approximation, right? Because you might use the value plus the value of the derivative to come up with a quadratic function to do things. In quadratic interpolation, so what is linear interpolation? Well, for linear interpolation, you have 2 points, and you draw a straight line between it, and you use that straight line to give you your approximation. To do quadratic interpolation, you need 3 points. You kind of need 2 to sort of to give sort of the basis for which direction you're going, and then you need a third kind of to give you some sort of some curvature. Okay, so the person who we're looking at is Ibn Yunus, and he wrote this Zij al-Hakimi. So Zij, remember, just means like is this Persian word for thread. It just came to be what you call table of trig values. And al-Hakimi, he was the caliph in Cairo. So this is the Fatimid dynasty, which was another one of those things that broke off from the Abbasids. Basically, Egypt became the Fatimid dynasty. And he used R equals 60. Okay. But if you think for a moment, what's the difference between using R equals 60 and R equals 1 when you're doing things in sexagesimal? Why isn't it that hard then to deal with that? Why is it that not much difference? Yeah, I mean, it's like for us working with 10, you know, like when you multiply by 60, it's exactly the same number. You just move the sexagesimal place. So again, you can see why there's no great clamor to unify the sign functions, right? Because using R equals 60 and R equals 1, you can use the same tables. You just have to be careful about where you're putting the sexagesimal place. Okay. So Ibn Yunus noted that when you use in linear interpolation, you always underestimate the function. And that makes sense because what do we know about sine from our calculus days? What kind of function is sine? Why does secants lie below the function? Okay. Yeah, it's to do with concavity. Exactly. So it's this picture here. And remember, sine is always a positive function, so we don't have to worry about, I mean, this is not true when it's negative, because then it lies above, but no, since it's like humps, it's always positive, linear interpolation is always going to lie below the actual values. Okay, so now you want to do a quadratic interpolation. How do you go about doing it? So remember, you've got your tables, and your tables come in equal intervals, right? 1 minute, 1 minute 30, 2 minutes, no, I'd say 1 degree, 1:30, 2 degrees, 2:30, 3 degrees, etc. And so you're using 3 equally placed points to come up with an interpolation. So Ibn Yunus did a very smart thing. So basically what you do is you do your linear interpolation and you use that to do an estimate, and then you do a quadratic correction. You take into account that the curve is actually above. And if you think about what the quadratic correction is, it's going to be precise at the endpoints. That's going to be the roots for your quadratic approximation. And so if you've got a parabola and it's got 2 roots, and let's just say it's shaped like this, where is the maximum going to be? So if you've got, you know, the 2 roots, where is the critical point of the parabola? The midpoint. And that's exactly, so the roots and the critical point are exactly the points that you're given from the table. So even though doing a quadratic interpolation sounds really scary, you're given the 3 points, you're given 3 easy points on the parabola. And that's what he proceeded to do. Okay, so we need 2 points for linear interpolation, 3 points for quadratic interpolation. So we've got 3 evenly spaced points. We've got some degree, that degree plus 30 minutes, that degree plus 1 minute. So Ibn Yunus used a set of tables that were every 30 minutes. Okay, so it's different from the tables that we saw earlier. Okay, so we want to find an approximation to theta plus k minutes. where k is something between 0 and 60. Okay, so we look at the linear approximation between the two endpoints on our scheme. That gives us a straight line. And we know that the linear approximation is going to be below the true value. So what we do is we approximate sine minus that linear approximation by a quadratic function. Okay, so basically we're getting this. If we subtract this from sine, what we're going to end up with then is something like this. So this is sine minus L sine. It's going to be this. So here is going to be at theta. This is going to be theta plus 1. And this is theta plus 30, the midpoint. And that's where the height of the quadratic approximation is going to be. Not necessarily where this maximum is going to be, but it's going to be the maximum of the quadratic approximation. Okay. So we know the roots. We know here and here. And we know here. So this thing here is going to look like some constant A times K times 60 minus K. Okay, so we're doing things in terms of minutes here. So in fact, we're making this point here the origin. So we're not taking care, in interest of the theta, we're doing it solely in terms of the minutes that we're adding to theta. Okay. So we know that the maximum occurs at 30. So the maximum of this is going to be 900A. We're trying to find what A is. But we know what 900A is, right? It's the difference between the sine and its linear interpolation. So we solve this for A. Okay, and so what we're going to end up doing is we're going to define the base for interpolation to be 4 times the difference between sine and its linear interpolation. You might say, where does the 4 come from? What we're going to do, we're going to divide by 900. And, well, let's make that 900 into 3,600. If we do that, we need to put a 4 there. So 1 divided by 900 is 4 divided by 3,600. But 3,600 is exactly 60 squared. So it goes from treating minutes like minutes to treating minutes like whole numbers. That's what happens when you divide by 3,600. Okay, so that gives us a procedure. So first thing is we use a linear interpolation to define what is the linear approximation of at the midpoint and at the point that we want. We then look up the actual value of the midpoint. We calculate our base. We then calculate this thing here. And that gives us our quadratic approximation. We add to our linear approximation a quadratic correction. So let's do the same thing that we did before. Let's do sine of 1 degree 22. So recall the actual, we know what the actual value is. I actually went to a calculator and got the answer and converted it to base 60. And remember, this was the value that we got when we used Al-Biruni's linear interpolation based on knowing every 15 minutes. Okay, so let's go ahead. So we know sine of 1 degree, so that's our table. So we figure out the linear approximation at 1 degree, 30 minutes. Okay, so we take the value for 1 degree and we do 30. We do half of the difference between the two. And so we end up with that linear approximation. Then we get the linear approximation for 1 degree, 22 minutes. Right, we get, again, we start off with 1 degree and we add 22 minutes times the difference between 2 degrees and 1 degree. Okay. We know exactly what happens at 1 degree, 30 minutes. It's this, and this was our linear approximation. So B is 4 times 0013. So we get 52. So that is the quadratic correction. Sorry, the base for the quadratic correction. So the quadratic correction then is 52/3 times 22 minutes times 38 minutes. Okay, and we keep track of everything we're going, and then I convert that to the quadratic correction. I add that to our linear correction, and I get the quadratic. And if you compare them now, you see that you get so 43. So 43.24, here we get 43.32. So we get a much more accurate answer using quadratic approximation every 30 minutes than we do with a linear approximation every 15 minutes. That's not surprising. Okay, so we get a lot less loss of accuracy. And so using this, you can do much better interpolation. Okay, so this is kind of useful. This is a lot of effort if you're doing it just to find 1 degree, 22 minutes. But if you're actually making tables, this would be kind of a good way to find values between values rather than using linear approximation, since it leads to a lot less loss of accuracy. So this is a good technique to actually create tables rather than use tables.
Okay, my first question is, on number 1, you have the linear approximation to 1 minute and 30 degrees, or 1 degree and 30 minutes. Why do you need the linear approximation when you actually have what that sign is?
Remember, this is giving us this height here. This is giving the correction for the correction for the quadratic. So what we're doing is we're finding this value here with the linear approximation, and then we're kind of we're approximating this distance here. And so what we're trying to do is we're trying to approximate by using a second order curve above here. And so that's going to more closely fit the sine curve.
Okay. And then I just got really lost. If you go back to the last slide, I just got really lost on steps 3 through 5. Like,
okay.
I think it's all the numbers that are there.
Yeah, it is.
I don't know what it means.
Okay, so what you're doing is with the linear approximation, you're basically figuring out what the x-axis is. Yeah. Okay, so that's your base. That's the linear base. And so if you just use this you would get values based upon the linear approximation. So what we're doing now is the fact that in reality, this value is here, this is accurate, this value is here, and it's accurate, and this value is here, it's accurate. So now you just want to put a smooth curve joining those 3 points. So the smooth curve we choose is a quadratic curve. And so that's the curve here, right? Because it's 0 at 0 and it's 0 at 60. So that's a quadratic that has those 2 roots, right?
Yeah.
I mean, that has roots 0 and 60. So now you want to make it go through this point here. And the reason why that's easy, straightforward, like in general, it's hard to figure out, given 3 points and find the quadratic through it is actually a non-trivial problem, you can do it. But because you're told that that's the maximum, we know then that the maximum is going to happen at k equals 30. Right, just because that's how quadratics work. Right, because the parabola, the critical point is always halfway between the 2 roots, no matter what. Okay, and so that means the maximum value is 900 times A, just by plugging in 30 to this number here.
And what's your A?
A is what we're trying to find. So we're fitting a parabola. And so if you think about it, we need 3 things to figure out a quadratic equation, right? We know 2 of them because we know the roots. So this tells us what the roots are, okay? And now we've got to find out how much we've got to multiply that by. What's the scaling factor, right? Because all parabolas like that look the same. It's just the scale. How much do we blow it up or shrink by? So we blow it up or shrink it by A. So the biggest value is going to be 900 times A, because when we plug in k equals 30, we're going to get 900A. But also we know that the biggest value is the difference between sine and its linear interpolation. So that gives us a number. And now we can solve for A. And that's what we've done. That's what we've done here. Okay. And so then we just get the linear approximation. That's this value here. And now we're just adding what the quadratic correction is. And that is going to be this here. And so this is a point on the parabola, and it's very close to what the actual value of sine is. So they developed really good techniques in order to be able to do interpolation. Okay. One last thing.